Okay, and we're live, I think.
Hi, everyone. This is David Greenberg from HZG, and welcome to, if I'm not losing count, the 23rd episode of the
It's the 24th already, I think.
24th. Goodness gracious, how time flies. The 24th episode of the Machine Learning at Helmholtz-Zentrum Gesellschaft seminar. We have a really exciting agenda today. We've got a brief presentation by Felix Stieler on recent machine learning work from DKZ. And then we have an interesting paper which kind of gets back to a lot of the great stuff we did earlier in the seminar, where we're exploring interesting results in earth science, new methods, new findings. But in the process, we're also really uncovering some great building blocks with which to construct machine learning models. We're seeing new stuff, new layers, new objective functions, new techniques. And we're going to get back into that again today. We're also really lucky to have the first author of the paper, Gabriel, I hope I'm pronouncing that right, Franch, to help us figure it out. So we'll start up with Felix Stieler's presentation. Felix, you can take it away.
Yeah, hello everybody, I'm Felix. This is a brief presentation of work that I did at the University of Düsseldorf in my previous job. So what did we do? We did a gene annotation. Gene annotation very basically annotates substructures in DNA. DNA is a very, very long sequence containing of HZG letters, and you annotate basically 4 different kinds of continuous substructures. And we do this as a base pairwise classification. So basically for every letter we classify if it's one of the 4. And this is easier, but also only a subproblem. And this is the architecture we use. So it starts at the bottom. We input the DNA bases as in one-hot encoding. They get chunked up into 10 base pair chunks. Each one is processed in one time step of a bidirectional LSTM with 4 layers. So this is the colorful part. Then predictions are being made for each base pair, like just classically with the softmax, and then things get concatenated and we get the output. So it's basically an LSTM, a stacked LSTM. And these are the main results. So at the top is for animal genomes, on the bottom is for plants. So we evaluated with 186 animal genomes. And on the top left, in the orange, you see our the thing we benchmark against, which is a state-of-the-art gene annotator called Augustus, which is a hidden Markov model. And as you can see, so each dot is the performance according to this metric, which has been approved by the reviewers for each genome. And as you can see, we outperform Augustus by quite a margin on most genomes. Like basically, we only underperform with very small genomes. And similar story for the plants on the bottom, although there the distance is not like too large, but still noticeable. And then on the right, you can see that the tool we built like so far is also much less prone to fall off when the genomes are larger. So Augustus really does this, and it's a well-known problem with gene annotators. Then when the genomes are larger, the predictions get worse. So for the plants, it's similar, but the spread is also large. So final remarks. Just the main challenges we faced were like just gene length in general. They can be very long, especially for mammals, can be easily 50 base pairs. We had a very large, relatively large number of genomes. I mean, there are more than 250 published genomes, but still a lot of genomes to choose from. And we trained with 15 of them. Like choosing the basically 15 or the number was not obvious. there's a large variability in data quality, very large and very hard to understand properly. Like the main lessons, I think, like at least I drew for me, is like that just data matters just as much as models do. So, I mean, I would say even more probably. I would think like data first and then like models at some point. And like a really efficient tooling for pre and post processing really enabled us to iterate a lot, look at the data from all kinds of different ways, and run as many experiments as possible, basically, to figure out what works and what not. And just more data is great, but if the data is not good, it's not great. So in the end, you want to generalize, and for that you need a clear signal. And so it's a trade-off between quality and quantity that is not obvious. So, yeah, that's it.
Thanks a lot. That's a really interesting topical deviation, but I think a lot of the same methods we're interested in. We have time for maybe one quick question if anyone wants to ask. We'll make sure to post a link to the original paper in the summary on our website. If there's no questions, I'll quickly ask one brief one. So you're dealing with very long sequential data. Did you have some way of speeding up the computation so it didn't have to, go step by step over these very long sequences?
Yeah, so one thing that we did to speed up the computation was to chunk it in those 10 base pair chunks and compute at each time step, like for 10 base pairs, and also predict for 10 base pairs at a time. So with that, because there's speed-wise, you're mainly constrained by the number of time steps you basically do, because they have to be done one after another. So if you can do only a 10th of the time steps, you basically cut it down by 10x, basically, almost. And I think that was the main thing. And also there's a limit to how far things can backpropagate, how long the dependencies are, how long dependencies can be learned, basically. And that also really helped with that.
Okay, thanks a lot. I guess if anyone wants more details, we can look in the paper itself. Toby, if you're going to start with your presentation now.
All right. Yeah, thank you for that presentation again. And today we're actually at episode 24 already. And today it will be about model stacking and about recurrent neural network architectures and about a paper that really clever combines all kinds of little techniques to a really neat product. And I'm really happy to have Gabriele Franch here as well, the first author of the paper. And again, please feel free to chime in every time or any time you want and add something. So to go over this today, I structured the talk a little bit into a few different topics. First, I would like to give a little refresher on recurrent neural network architectures. We covered them in episode 3, I think, with the MetNet, and that's quite long ago, so I think a little refresher wouldn't hurt. And furthermore, I would like to introduce 2 new concepts which combine temporal and spatial recurrency. Then afterwards, we'll talk a little bit about model stacking, which is something that is super common when being on Kaggle or on any data competition sites, or actually anywhere where machine learning models are used in applications. But we rather see this, we seldomly see this in scientific applications, and we'll talk about why that is. And last but not least, we'll talk about the real thing we're here for today, the main paper, Precipitation Nowcasting with Orographic Enhanced Stacked Generalization, Improving Deep Learning Predictions on Extreme Events. So let's start with the refresher. So maybe first ask, or maybe hopefully answer the question, why do we even want something like temporal recurrency? We all probably know convolutional neural network architectures and structures, which have the advantage of being able to exploit spatial structures by not only using pixel-wise information, but as well looking at a certain area around a single pixel. We call this usually the receptive field or something like this. So we have something that really can exploit spatial structure already in images, and most of us have used probably something like this when we have used neural networks before. There's something similar for temporal structure, which is called RNNs, recurrent neural networks, which has the ability to look at previous time steps and use these informations of previous time steps to maybe make predictions in the future or extract other features from these time steps. And then there is something that combines both of these ideas. And these are especially the ConvLSTMs and the trajectory LSTMs, or trajectory gated recurrent units. And especially when we deal with data of meteorological or oceanographic data, we have these fields which have like spatial information, but they vary over time, like a video. So we really want to exploit both of them, the spatial and the temporal structure. And ConvLSTMs and trajectory gated recurrent units really excel at that. So when talking about recurrent architectures, usually one talks about LSTMs and gated recurrent units these days, which all developed from the vanilla recurrent neural network unit. We have to think about all these architectures as some kind of layers, which we can just use as convolutional layers in a network. So they don't form a complete network, they're just part of a network. Right, so if we then want to use temporal and spatial information together, we use, like I said, these ConvLSTMs and trajectories, which both were invented by Xingyang Qi, I hope I pronounced this at least close to right, et al., which looked at precipitation nowcasting as well. So this really is something coming from meteorological driven background and being developed in the machine learning world. So maybe let's first look at the simplest form, the recurrent neural network. How does that work? It works by having a single input, applying some transformation and a tangent hyperbolicus layer, and then having this output. But the output is saved in some sort as well in the hidden state. And we can then put the output again in the network together with a new input. And we can visualize this as if we would put several layers, one behind another. But actually, this is just one layer, and we put the same, or the sequence of data in there, one after another. And therefore, for the network, it is possible to use information from previous time steps to do some sort of information extraction or prediction in these parts. The problem with these RNNs is they have really problems with the backpropagation, because usually deep neural networks are trained with backpropagation. And the larger the sequences get, the more the network just relies on the very last layers of these RNNs, the very last inputs, and the very first ones might even be disregarded. Why that is might be a bit too much for now, but just keep this in mind, because that's why the other forms of recurrent architectures actually have been developed in the first place. Here it is. After the recurrent neural networks, LSTMs, long short-term memories, were developed. Like I said, RNNs had problems with the with inputs further in the beginning of the sequence, these ones, and therefore it said they had like a short memory because they only remembered the last things. And long short-term memories tried to fix that. And they do this by introducing a complete new state to the cell. Now we don't only have the inputs and the outputs, but we also have a complete separate hidden cell state. And this works by putting in some input. Then we have three kinds of, they are called gates. This is the forget gate, this is the input gate, and this one is the output gate. The forget gate tells the hidden states whether it should forget everything that it previously has saved or not. And this is done because here is a sigmoid activation. And the sigmoid activation scales everything that gets in there between 0 and 1. So if it's 0, we multiply our hidden state by 0, meaning it forgets everything because everything multiplied by 0 is 0. And if we want to remember it, it's closer to 1. And we do the same thing for the inputs and the outputs. And therefore it is able for way longer sequences to remember stuff and to rely on inputs that are very at the beginning in the sequence. So it is possible with LSTMs to process longer sequences than with RNNs. But the downside, on the other hand, and I think that's very easy to see, is that we have way more computations and way more memory use. So we are more limited in our structure, therefore. To circumvent that, gated recurrent units are introduced, which are a bit more in the middle between both of them. Now we don't have real output anymore. We only have the hidden state, which is the output. So we got rid of this extra state, which we had in the LSTM. But due to some clever gating again, and this one is called the reset gate, and this one is the update gate. So now we only have 2 instead of 3 for the LSTM. We are able to actually use longer input sequences again. So they are about as capable as LSTMs, I would say. The difference is, again, these are computationally more efficient, I would say. But a machine learning practitioner usually would try out both of them and see which works better for the given problem, because the problem, like we have heard in the previous talk, the data is more important than the model. And so you really have to adjust to the data and try out everything you can. So now that we kind of understood how a gated recurrent unit or an RNN might work, we can see how we could actually, or why we need an addition for being able to recover spatial structure in here. Because what I didn't tell you yet is that the inputs and the hidden states are all one-dimensional vectors in the RNNs, the LSTMs, and the gated recurrent units. And that is because all these operations in here to calculate the matrices are only allowing for one-dimensional vectors because these are point-wise multiplications. And what Jingyi, I can't pronounce this name, I'm very sorry, now did, they changed the operations, the point-wise multiplications, to be kernel convolutions, therefore allowing two-dimensional inputs to be processed. And this then allows for spatial structure not being destroyed because we don't have to flatten everything, we put it in here. Then there is just one more escalation step to these, because what LSTMs or convolutional LSTMs only allowed for fixed connections. But this is not always what you want. Let's think about the weather pattern over Germany. Usually we have something like a westerly flow. So if you only look at the pixels westerly to where you actually want to make predictions, most of the time you're really good. But when the flow changes and now easterly, you're still looking only at the westerly pixels and therefore missing the most important information. Therefore, trajectory-gated recurrent units and trajectory LSTMs have been developed, which allow for adjusting where to look for information in the previous frames. So in a very wide sense, like, yeah, it might be a little bit comparable to attention, where we learn where to look at for information. I hope I didn't lose every one of you now, and I hope you got a little idea of how these traj grooves work and why we actually want to use them. That's way more important, not how, but the why. So the next thing we need to understand today's paper is model stacking. And we have not covered this, I think, at all in the machine learning seminar yet. Model stacking maybe start without stacking first. So our usual workflow as a data science practitioner or machine learning practitioner is we have some data, we want to gain some information out of it, therefore we develop some model. The problem often is, which model should we use here? I mean, this could be anything. This could be a deep neural network. It could be something like a decision tree. And usually what we would do is we have an intuition and try what our intuition fits and then try maybe some different approaches. But there's something else which we could do, and that is, why not train all the models that we have in mind? Why not train a decision tree, a random forest, a deep neural network, a boosting algorithm, just something, and train all of them on the data? And after we've done this, we train an additional model to use the predictions of each of the separate models to make a final prediction. That way we get the best of every model, because maybe the deep neural network is very good at classifying or finding the dogs in the image and saying it's a dog, but maybe the boosting algorithm is better than in finding the cats or something like this. And the meta learner, or something that's called the level 1 or the level 2 learner, then learns where all these models excel and puts together the best of them. And what we can then do is we can even add additional data to this meta learner, which we might have not added to the base models, maybe because it was not available here or it didn't suit the structure or anything, but there could be many reasons for it. Then there is another method for model stacking, actually. So we've talked about stacking the models themselves and training all the models on the same data. But what we could also think about is not training on the same data, but splitting the data up and training the same model on different parts of the data set. So why would we want to do this? Imagine you have a very small data set and you want to train maybe a very deep neural network on it. Then you have a very high chance of overfitting on this part of the data. And what you can then do maybe is split the data set into many parts, many chunks of the same size. So which shows here 7 chunks. 2 of these 7 chunks you set aside already from the beginning. So you're left with these 5 chunks. Now you can always combine 4 of them to be a training data set and leave one out to validate this. So we train our first model on this training data set consisting of A, B, C, and D, and then validate it on E. The second model has the exact same structure, the same laws, everything stays the same, but it is trained on B, C, D, and E, and is evaluated on A. And so on and so on. So we can have many different models, create an ensemble of models, and afterwards we create a completely new one, which learns to combine just the best of each model. And therefore we have set aside at the very beginning this extra data set only for training the meta learner, and at the very end testing the complete ensemble model. That is stacking, and like I said in the beginning, this is seen very often and very commonly on data competition challenges like Kaggle or Driven Data or something like this, because this is usually able to give you like another 1% performance increase or whatever metric you want to increase or decrease. So it's not a completely game changer in the very most parts, but if you're after the very last bit of performance, this usually can give that to you. This method might be familiar to some of you, maybe when you're familiar with k-fold cross-validation. At k-fold cross-validation, you would do quite a similar thing, but always training the same model and not new models. So maybe that helps you understand that if you're familiar with k-fold cross-validation. All right, so I hope you got a little bit now what a recurrent neural network is, that we want to use recurrent structures combined with convolutional layers to exploit the temporal and the spatial structure of our data by using something like trajectory-gated recurrent units, and that we can stack many models together with a new meta learner to make even more powerful predictions than each of the models could have done on its own. So today's paper and I think I called the title already, Precipitation Nowcasting with Orographic Enhanced Stacked Generalization, Improving Deep Learning Predictions on Extreme Events. And we should really look at this focus here, improving deep learning predictions on extreme events, because it is, I wouldn't say it is quite easy, but it is way more easy to make predictions in nowcasting for light precipitation. The problem with extreme events is that they are so rare in these data sets. And therefore, we have usually a high bias in these data sets against light precipitation. And we will see how the authors of this paper tackled this with a very clever approach, not by making the data set unbiased, but by changing the loss to account for this biased data set. So what are the main targets of this paper, in my opinion? They tried to forecast the next 100 minutes of precipitation of radar data using the past 25 minutes. To do this, they use an ensemble, so a stacked model of trajectory-gated recurrent unit models, or models that include trajectory-gated recurrent units. Then they add in their meta-learner extra information about the orography to make the model even more powerful. And all of this is compared to something that's, I wouldn't say it's state-of-the-art, but it's what is applied at most weather services. It's Lagrangian persistence. So for the machine learning people, it's really comparable to optical flow. And you can think about it as you only move precipitation patterns along the wind field. So this method is never capable of accounting for rising or vanishing precipitation, really. So the data that has been used to train the model or models is these radar data. I think it's over the southern Alps in the northern part of Italy. And the images are 480 by 480 pixels. And because of we're using the last 25 minutes, this means because of the 5-minute resolution, we have 5 input images like this. And the area that is covered is 240 by 240 kilometers. And what the authors did is they looked at the data from 2010 to 2019 and first looked for sequences where they have precipitation and excluded all sequences that don't have precipitation at all because we don't need them to train on them. Then they furthermore extracted these sequences. A single, like one sequence is one training target, you can say. And so they have 190,000 sequences for training the ensemble members. Then they would validate them on 10,000 sequences each. For the meta-learner, like the model that comes after the ensemble models, they used the time after 2017. And then to evaluate the ensemble, so the complete model, like the result, they hand-selected the data to include more extreme case scenarios. And I think that's very nice because they are focusing on extreme case scenarios, like they said in the title, but by changing the proportion in the test set to include even more extreme case scenarios, they made it even a little bit harder in the testing than in the training. Okay, so how does one ensemble member look like? I told you before, when doing model stacking, we can either change the data or we can change the models. But what the authors of this paper have done is even something a little bit different. So they all used the same model, and this is the model structure they used. It's called an encoder forecaster model, which has been introduced by Qingyang Qi, I think. And it works by having some downscaling part and some upscaling part, very similar to the unit structure. But in between the convolutions and the deconvolutions, we have these recurrent neural network layers, which in this case are trajectory-gated recurrent units, the ones I showed you before. Therefore, we can downscale the image and increase the channel size, like in a unit, to do some form of encoding, but keep the information, the temporal information of the encoding at each downsampled state with these RNNs. And we do the same in the other direction for doing the precipitation, for doing the predictions later. We upscale the image and we do the upscaling by transpose convolutions. So as far as I understood this, there is no linear layer in here. Everything is convolutional. And that way we completely keep the spatial structure of the images. Now, you've seen now what a single ensemble member looks like, but I said to you, they neither change the model, nor they change the data. So how does the ensemble actually create it? And to see that, we have to have a look at the loss function they are using. It actually is very simple in the beginning by just adding a mean squared error and a mean absolute error. And we do this pixel-wise. So that's something that's very common in many machine learning applications and when training deep neural networks. But since they have this very high bias towards hardly noticeable rain, so rain that is only between 0 and 0.5 millimeters per hour, and they actually would like to focus on extreme and heavy events, but this is like nearly not noticeable even in this large data set, they had to make something to account for that. And one thing they could have done is they could have just excluded a lot of this rain to make the data set more unique distributed, right? To have more events with extreme precipitation relatively. But they did something else, which is they included some weighting in the loss function. And the weighting is dependent on how much or how high the precipitation is at the target. So if the target has nearly no precipitation, then we'd only give a very low value to our loss. And if the target has lots of precipitation and is an extreme event, we really weight that loss like really high. So if we are thinking about a neural network that is at the moment really bad at forecasting an extreme event and even only makes the mistake of 2 millimeters per hour. And then this 2 millimeters per hour here will be multiplied by 30 after even being squared. So the punishment for being wrong in an extreme event is very high, and therefore the network really tries to more emphasize extreme events. And now we still don't see how this really creates an ensemble of models, right? I just show you how they deal with the biased data set. But you might have noticed that there is a little t in here. So R of x means the rain rate. And the rain rate is in millimeters per hour. But we have a little threshold here. And the threshold can be adapted. We can use any amount of threshold that we want, but it should be lower than 2 to actually make sense here in the first case. So we say we only calculate a loss if the target precipitation is larger than one of these values. For the first ensemble member, we say if it's larger than 0.03 millimeters per hour. For the second member, we say if it's larger than 0.06 hours. And therefore, all these different ensemble members only start to look at or really learn the parts of the precipitation when they are over the threshold. And the only other thing that you can see in here is they also have this mask. And as far as I understood that is some kind of clutter mask that is static, which means this will exclude pixels from the very beginning, and this is not learnable or anything adjustable at all. Because we're in an alpine region with lots of mountains, we might have areas where the radar might not look over at, or something like this. So the mask excludes these pixels.
Yeah.
Thank you very much.
The exclusion mask, it's done only to exclude pixels that we know there are too noisy, let's say, in the data itself. And this is done, and to exclude all the pixels that are outside the radar circle because the radars can't. We have
Oh,
a
right.
circular shape, right?
So
we need to
yeah,
exclude
so all
the
that's out
outside
here,
pixels
right?
also. Yeah.
Ah, yeah. Okay. Yeah, thank you very much for chiming in there. Okay, so each of the ensemble members learns something different, and we can see this very nice at this plot. And we don't see any metric here, so the line plots don't tell us how good one of these model ensemble members is. It just tells us that they all learn different things, really different things. And I don't want to spend too much time here, but we can see that especially for the ones with a high threshold, the average pixel values seem to be lower. Other way around, I'm sorry. Low pixel values for the one with a low threshold, and higher pixel values for the one with higher pixel values. And this really intuitively makes some sense, I think, because the model focuses more on heavy precipitation when it can't see the light precipitation, like here.
This, if I may join here, just a second. Yeah, this is important. It's not that the model does not see the precipitation. So we input the whole precipitation exactly the same data to each one of the four models. It's just that it's not, it's punished, let's say, it's not punished for not predicting correctly the very light precipitations. So this, I think that this is important because we do not change the data in input of each one of the ensemble member. We want the models, all the four models, to gather as much information as possible from the input. So we do not exclude anything from the input, but we change
but you
the
just
loss.
set this to 0, right?
Yeah, exactly. Yeah, but this is in the loss, so it's not in the input.
Yes, right.
It's also in the loss calculator. So the model sees all the precipitation in the inputs, but it is not punished for, let's say, for having wrong prediction on very light thresholds of precipitation. So,
you're totally right. I might have misformulated that. Yeah. Thank you. So we can actually see that all the ensemble members do something different after being trained. And now we can exploit this by model stacking. That's why we talked about this before. And here we do this by having this meta learner, which consists of 5 blocks. And each block has 5x5 convolutions, batch normalizations, and a preloop activation functions, which is a reloop but continuous. And because they only use strides of size 1, we don't have any downscaling here. So the spatial size of the inputs is preserved throughout the complete process. What they then did is they not only included the outputs of the ensemble members, but also added orographic features. They added an elevation map, orientation derived from the elevation map, and I think this is like the slope in percentage, if I remember correctly. So they stack all of them together, making it like a 7x480x480 input, and then doing the final prediction with this this meta learner. Okay, let's have a look at the results. So what can we see here? First of all, we might have a look at the CSI, which is the critical success index, or in machine learning called sometimes the threat score. And it is some sort similar to, or it's a concept of accuracy actually. So we divide the hits by the hits, by the hits, the misses, and the false alarms. And when doing heavy precipitation predictions, especially with MSE and MAE, usually the misses are really high. So to get the CSI, to get better CSI for high values, we really want to reduce the misses. Okay, so CSI is a score and it maxes at 1, and the lowest score you can get is 0, and the higher is better. What can we see here now? The different colors are the different models, and the blue shades mean the different ensemble members. We have the green one, which is just an ensemble average. So if we hadn't trained this extra meta learner and just took the average of all the ensemble members, then we would have gotten the green one. Then we have in yellow the ensemble plus the meta learner. So this one, but only with the inputs and not with the orographic features. Then we have in orange just a single member plus orography. So if we had just used one of the members plus the orography features, and this is done to see if we actually gained something from using the whole ensemble. And then in red, this is the final product using everything, meaning it uses model stacking, all of the ensembles, and the additional meta information of the orography. And all of this is compared to the gray one, which is the Lagrangian persistence model, the optical flow stuff. So we can see from the first few really that in the very most cases, nearly all of the machine learning and deep learning architectures outperform the optical flow stuff. And this is not really surprising when thinking about that the machine learning models are able to capture rising and vanishing or precipitation, which is never possible for the SPROC model. But what's really interesting here as well is we can see that when we compare the orange one, which is just a single model plus the orography, to the ensemble plus orography, we see there is not a lot of difference, at least when looking at the CSI. This is just one score, keep that in mind. There are other scores, but when comparing the critical success index, it looks like we don't really gain a lot when using the ensemble. And this is a bit what I said before when I talked about model stacking. We can see there is an increase, and there is an increase regardless of the threshold we are looking at, but the increase really is small. So we use model stacking usually when we're after this last % of performance increase. And we can see as well, even though this paper really focuses on punishing the model when precipitation in the high areas is wrong, we can still see that there's lots of improvement for high precipitation. And now we can ask why the optical flow method is so good compared to the ensemble method in the high precipitation areas. But when you think about this, the deep learning models are trained with MSE and MAE, which means that heavy or high value areas usually are flattened. That means that the deep learning model usually gets closer to some mean the further you progress in time, while the advection model always preserves the amount of rain and therefore might be able to preserve some heavy precipitation areas. On the other hand side, and we can see this at this last slide, very good. Now we see here the observation, which is the ground truth at the top row. The 4 rows below are the different ensemble members. Then we have the ensemble average here. In the second last line, we have the optical flow model. And the last line is the final product of the paper. So, and if we especially compare the optical flow method with the final product, we can see one thing that really got into my eye when I looked at this. In the ground truth, we see that there's some rising precipitation pattern in the upper part of the radar image. And since this method is just moving existing precipitation patterns along some advection field, it is not able to capture the rising precipitation pattern at all. It is, on the other hand side, quite good at following this heavy precipitation pattern quite far into the future. The machine learning model, on the other hand side, really captures this rising precipitation area here at the north quite well. On the other hand, therefore, underestimating this heavy precipitation at the bottom below. So I think here we can really see that machine learning models do increase our forecast, the value of our forecasts, even though when sometimes looking at single scores, one might not see this at the very beginning. And if you have read the paper, there are lots of more scores they compare their models to, showing why the ensemble actually really makes sense to use here. And I think that's it for today. I hope you learned something, and maybe Gabriele, you want to add something at the end, or not? Otherwise, thank you very much for attending this meeting and chiming in now and then.
Thank you. Yeah, if I may add, one thing that we try to improve, it's I have, say, we did some new plots to show what actually we were trying to improve, other than just improving, let's say, the critical success index. What we were really trying to do is we were trying to improve the bias in the let's say improve the bias, improving, let's say, improving the frequency bias of the prediction. So force the model to predict more pixels, let's say, with higher precipitations. Okay. And if I may share, maybe I give you an idea of why the model stacking it's really worth for this kind of when you want to predict the extremes, especially, so very rare events. I have plots that maybe it's useful to understand. That
Do you want to share your screen?
If I can, yes, I can.
I don't know, David, you might have
I
to...
just made you a co-host, Gabriel. You should be able to.
Let me see if I can. Okay. Check if I can. I'm sorry if you hear noise, tell me, because I have the workers in my house today. I wasn't expecting to present.
Don't worry, we're all in home office at the moment.
See. Can you see my left screen?
Yes.
Yes.
Do you see the presentation?
Yes.
Okay, so if you look at this plot, this is the CSI contour plot. So it's a plot that puts together, let's say, 4 different measures that you can compute on, say, on this kind of problem. So you have the critical success index, which is represented by these contour lines. Okay. And on the y-axis, you have the probability of detection. And on the x-axis, you have the false alarm rate, so the ratio of false alarm. And then you have these diagonal lines here. These dashed diagonal lines. These lines is the bias. It's called the frequency bias. So the frequency bias, let's say that if the result of my evaluation is over this diagonal line, the middle diagonal line, I am overrepresenting that particular rain rate threshold in my prediction. Otherwise, if I am below the diagonal line, I am underrepresenting the number of pixels with that particular rain rate threshold. And here you can see the performance of the four ensemble members and how they show this conditional bias. The conditional bias is that we are overrepresenting the lower and mid rain rates, basically, but we are severely underestimating the number of pixels with high rain rates. Okay? And this is the typical problem of training a model using, some kind of averages, which is usually what you do using deep learning. We use either MSE or some kind of mean, let's say,
Right.
especially on very skewed distribution data. So you incur in this frequency bias problem where you are overestimating lower part of lower, let's say, lower values, and you're overestimating lower values and underestimating higher values. So we wanted to fix especially this part, because we are using this model operationally for civil protection purposes, and the civil protection is interested in high impact events, which are those one, basically the one that you see on the lower right side of this plot. So if we zoom in, like here on this side, we can appreciate how the stack generalization is able also not only to increase the skill, okay, but also to reduce this let's say, to improve this frequency bias. So to make the model predict more pixels, let's say, with higher rain rate. I'm going to add all the other models with the same colors that you've seen. So this is the ensemble average, and this gives you a good idea why usually the average improves. So taking the average improves a little bit the scores on the lower rain rates. You can see it here. Okay, the average is better than the others. So it's more near to the top left corner, which is where you have better scores, better prediction skills. But when you go to higher rain rates, if you take the average of four numbers, you're flattening you're flattening basically the peaks. So the average is not actually a solution for improving on the extremes. And here we start to see the contribution of the four ensemble members. So it has a better bias, a little bit better bias, especially. So it's predicting more pixels with higher rain rate already. And then as soon as we add the orography and then the orography plus the ensemble, we recover a lot of bias respect to all the other possible models that we tested. So, and here you can see the performances of the Lagrangian extrapolation. So the Lagrangian extrapolation, it's exactly as you said, quite good in the higher rain rates, because it's able just to persist the current situations in the future, basically. So it persists the current frequencies of the events in the future, and by doing this, it's often better than the other deep learning models. So, but if we look at the final results of combining the ensemble with the orographic data, we can see that we have a much better bias, and not only a better score, but also a better bias respect to the Lagrangian extrapolation. So yeah, that's basically the things that we wanted to do. So we wanted to have a model that keeps all its skill power on the lower rain rate. So we don't want to lose the ability to predict the lower rain rates, but we want especially to improve the prediction of higher precipitation, especially by reducing this let's say, improving this frequency bias, basically. Okay. So, and
to me it looks like on the way you improved on the low frequencies as well, right?
Yes. We have improvements in both skill and actually bias on the low frequencies. But what we were really interested in was to improve here. And here we have like 140% bias reduction over all the four ensemble members, over the blue ones, using the stack generalization. So it's a huge improvement in the bias part. So not only the model has a better, let's say, a better skill, but it's also predicting more pixels. So it's predicting more pixels on the higher thresholds, and it's putting them in the right place at the right time. Okay, so it's even more difficult to increase both the frequency bias, let's say, to have a better frequency bias and a better skill score at the same time. So yeah, here you can see an example of one of the ensemble members and the stack generalization, especially on those red parts are the one that we were really interested in. And this is a particular moment that we had on our test set, which was the day that a town was completely flooded by these heavy precipitations, and you get an idea of what we were trying to nail down in this huge data set, let's say, to improve these kind of situations. Okay.
Right.
Okay, I think
Yeah,
I
really-
can stop it. Okay.
Really interesting. Thank you for that additional information. Really nice plots, by the way. So there are questions in the chat. No, David has a question.
I would have a question. Yeah, thanks for the great presentation, and thanks, Toby, also for that explanation. So, I mean, I have a comment and a question on this. So one thing that really struck me is the machine learning is pretty new. The TRAG GRU is 2017, and you're building on this. And I think the fact you have this in an operational system, which is actually used to help the public, is quite amazing that it happens in such a short time. But related to this, I'm wondering what are the actual kind of events, these extreme rainfall events that you want to warn people about? How would you define this in terms of quantitatively identifying these scenarios? And would it be something other than these pixel-based measures? You talked about getting the correct number of pixels above a threshold, which is certainly good. When you talk about an extreme event like a flood or a major storm warning, it sounds like you might also be interested in an extended region of space or an extended region of time. And does it make sense to kind of incorporate that in our accuracy measures?
Yes, you're totally right. Actually, the way we are using this operationally for early warning is actually by integrating the amount of water over time. So we compute we use the hydrological basins of the area, okay, and we compute the amount of water that it's falling down, that has fallen. Let's say that we are, let's say, sum over time the amount of water that is falling down in an area, and then we have, let's say, hydrological analysis that tells us how much water can fall down in that area before something is probably going to happen. Okay, so that's very important. We want the prediction model to be as precise as possible, so we don't want to turn this kind of problem into a classification problem, like you're over the threshold or not at that particular moment. We really want a number there that we can adapt over time to know we have reached an amount of water in that area that it's that we know for historical reasons. So we have, we work with the civil protection, they know their stuff about, all the hydrological studies of the different areas of our region, and it tells us the amount of water that can fall down here in this amount of time is this one, and above that we should sound a bell, like this is an alarm. So we have that kind of thing going on. So we use this prediction along with the observation. So we basically what we do, we sum over time both the past, so the observation that we have from the radar, and the prediction. And if we predict that we are going to go over certain threshold in a certain area, we can have the early warning going on that sends. We are using a Telegram bot, so we send Telegram messages to people. But these are going to to wake up people in the night also. So we really want this to be to be as precise as possible, because then people then have to take decisions on that. So yeah, that's the way we are using it. So we are not just using a particular instant in time, but we are integrating it over time, and we raise the alarms when a certain threshold, a certain accumulation over a certain a number of time spans it's has been accumulated, basically. Okay, so but if the model has a good skill, that's the point. If the model has a good predictive skill, then you can trust also the accumulation, okay, over time to be something that you want to use operationally for pre-alerting people, let's say. Okay.
Right. We have another question. Thank you very much. First, we have another question from Lawrence from Gerex.
Yeah,
Lawrence.
hi. Good afternoon. Thanks for the great presentation from both of you, and the great work in the paper. Really interesting. I had two questions. One is about the data you're using at the moment, orographic data, basically, to improve the predictions. Have you considered other variables such as humidity or dew point temperature or any other locally observed variables that might improve the prediction? And the other question is whether you could extend the time scale. Now you're predicting ahead 100 minutes, but is there potential to even make that longer?
These are two very interesting questions. The first one is yes, we are already working on that. We are already working on integrating other variables. At the moment, we are just using them as this. Let's say that this can be seen as a video with with just one channel, right? So we're trying to do like the task is similar to video prediction. You have this different that the data is very skewed, but let's say that the on the machine learning side, the task is very any improvements in video prediction models, we can incorporate that, right? Okay, so and the things that we are trying to do now, it's to with another project, we are working both with the civil protection of Trentino, so it's the Alps, but I'm working also with Bologna, so Emilia Romagna, and with them we are trying to do the let's say the multimodal prediction model. So we are incorporating actually lightning strikes because they are very we have them in real time and they are very precise in space and time. So this and they are very good indicators for extreme events, of course. But yeah, you can imagine to integrate also other variables. You have to, let's say, find a way to fit them in the, let's say, how do you integrate this kind of inputs in the models and so on. But at the very beginning, we are just adding new channels to our, let's say, images sequences, and each one of these new variables, it's a new channel, and we use the same spatial grid for each one of them. So we, let's say, interpolate them on the same spatial grid. So yeah, so that definitely is something that will help the model to improve the prediction target. Then you have the question that you can, I mean, it's something that we are still trying to understand. Are we going just to predict the precipitation then, or do we want to predict all the, so we take new inputs along with the precipitation, and we just predict the precipitation, or we want to also try to predict everything else, or this is, you know, decided up. I think that depends on the application that you have. Okay, but yeah, that definitely it's something that we are in the process of doing. Okay.
Really interesting question. I had myself too.
And the other
Thanks,
one,
Lawrence.
sorry, I forgot. I think I forgot the other one. There was another one. Okay.
Sorry, yeah, that was whether you can go beyond the 100 minutes prediction if you can make that long.
You can. It's not that you cannot, but it all depends on the spatial and temporal resolution that you want to resolve. On this model, we were already completely memory and compute limited. The input tensor to the network was like 5 by 4 by 480 by 480, and the output was like, because we had a batch size of 4, you need a little bit of batch size to stabilize the model during training. So you cannot just input one example. So you want to input at least 3 or 4 examples. So it means that the input tensor is something like 5 by 4 by 480 by 480, and the output feature map, it's 4 by 20 by 480 by 480. So these are huge input and output sizes. And also in the middle, since the trajectory GRU and convolutional STM models, they are whole, you know, 2D features maps in the middle. They use a huge amount of memory. Like we have to split the model in 2 parts: the encoder on one GPU, the decoder on the other GPU, and they're using both 16 gigabytes of RAM each. And you take 1 week to train the whole model. So it's also a matter of, you know, resource that you can put into it. You can, answering your question, yes, you can extend the prediction longer. But for example, also Google did that with MetNet, and they use this trick of conditioning on the target lead time. It's like I don't want to predict everything from let's say from now to my target lead time. I just predict the target lead time. So I just want a prediction like 3 hours in the future. So my input is this, give me the prediction 3 hours in the future. And this is interesting, and it allows you to extend the prediction target more, because you don't have this huge, let's say, at least output feature maps that you need to generate. But you have this problem, and you can see it also in their video, in the prediction video. It's noticeable that you potentially lose the spatial, let's say, the temporal coherence of the prediction. So it wobbles like a little bit. And let's say the civil protection that we're working with, they are very conservative on this kind of stuff. So they really want to keep spatial and temporal coherence in their prediction. So you also have operational reasons not to want to go that path, let's say. Okay, so keeping the spatial and temporal coherence in your prediction is also a feature that let's say meteorologists consider important. Okay. So yeah, it's still a lot of possibilities to develop, but you also have to deal with let's say a number of compromises that you want to choose. So
I think we have 2 last questions. Kubi, you have raised your hand all the time already. Do you want to?
Yes. So also first, thanks for the presentation. My question is about a possibility to combine maybe the Lagrangian persistence and the model. So my idea was, you said that in extreme events, the Lagrangian persistence is way better. So would it be possible to use the prediction of the Lagrangian persistence also as an input to the network to predict the future state, and maybe also look at where the 2 predictions differ a lot, and maybe that can give you strengths of both methods? Does that make sense? Or also is it feasible?
Oh yes, for sure. It will be feasible. I would say, and it could be interesting. So, and it also something that could have been done, let's say, also in this work. Actually, we added the comparison with the. I have to be sincere. We added the comparison with the Lagrangian extrapolation during the review. So we didn't do that, but it's actually something that can be done. Like you use the stack generalization to combine both the deep learning and the Lagrangian extrapolation. So that is something that you may want to do, and that could be helpful. Consider one thing: trajectory GRU already includes some kind of Lagrangian extrapolation. So the way that trajectory GRU computes these dynamic convolutions is actually by performing an optical flow step. So it's actually, so trajectory GRU actually integrates the idea of Lagrangian extrapolation to perform this dynamic convolution. So it already includes some idea of that kind of applications, of that kind of model. But yeah, it's something that definitely you could try to do. In the end, we saw that using this threshold ensemble was very useful. So we basically we went for that. So yeah, we let's say that with model stacking, you can do a lot of things, a lot of strange things. We also didn't want to add too many things to the stack generalization. We thought about adding, for example, other sources other than the orography or other stuff, but we wanted to keep it simple also to see if our idea really worked as expected. We knew that the orography had an impact because we are in a very mountainous region. The radar covers an area that goes from Innsbruck to Verona, so the whole Alps from north to south in the let's say. And from the meteorological literature, you know that there is an interaction between orography and precipitation. There is all this kind of stuff that it's called orographic forcing, let's say, that you know stops the precipitation or stuff like this. So we knew that there was a relationship between, let's say, our observed data and the orography. So we exploited that, and we wanted to see how much this added the let's say added prediction skill to our target. So that was also a test that we wanted to do. How much is orography a factor in predicting our precipitation, the precipitation sensed by our radar.
Yeah, thank you very much. I think we have one last question by Hagemann, and it is: how long does it take to make 100-minute prediction? I think this is like
so in inference. Okay, in inference mode, the model runs very quickly. It takes like 40 seconds. So we have a strict limit to take the prediction. So from when we receive the radar data, we have 1 minute and something to raise our alarm. So it takes 40 seconds to generate the prediction and or the trajectory group prediction on a normal machine like 4 cores and 60 gigabytes of RAM. So in inference is very quick. It's very hard. I mean, it's very long, the training part, but on inference, this is not a problem. It's just a couple of seconds. And then we compute all the threshold. We sum up the precipitation over time. We compute all the threshold, and if it's needed, we send the alarms through a Telegram channel. So it's just like that at the moment.
So you do the inference on CPUs?
Yeah. We have a virtual machine on Azure that runs every 5 minutes. It's continuously getting the data and generating the prediction every 5 minutes. Yeah.
All right. Yeah, thank you very, very much for joining today again, Gabriel. And thank you everyone for joining for today's seminar. I learned a lot. I hope you did too. And I hope we see each other next time in 2 weeks, probably on Tuesday at 3 again. So if there are not any last questions, which are really urgent, then I would thank you all again and say bye-bye.
Thank you very much.
Thanks.
Thank you.